The plan is to talk about the Magnetar observations that we did. And I would like to start with a nice sentence which I heard last year when Jocelyn Bell gave a talk at the German Astronomical Society. And she gave a talk on transient phenomena. And she said, magnetars do all sorts of funny things. And I can certainly subscribe to that. And hopefully by the end of this talk, you will agree to that. Let's start by saying, what are magnetars? Magnetars are, first of all, neutron stars, just like pulsars. And what differentiates them from pulsars on the one side is a very high magnetic field of typically 10 to 11 Tesla. That's about typically 1,000 times stronger than an ordinary pulsar. Another differentiator is they have a fairly low rotation rate, typically a couple of seconds. And they also have a high spin down, so the rotation gets slower. Now, 10 to the minus 11 seems to be fairly small. And if you call it high spin down, a pulsar must be lower in spin down. And it actually is. A typical number would be 10 to the minus 15. Or for millisecond pulsars, even 10 to the minus 20. Magnetars typically represent themselves as X-ray or gamma ray emitters, which occasionally flare. And only very few are actually visible in the radio regime. So most of them are not visible in radio. If they are visible in radio, they typically have a very high degree of linear polarization. And they also have a flat spectral index. Flat spectral index means that the decline of the intensity over frequency is flatter than for a pulsar typically. And magnetars are fairly seldom in the sky. There are only 31 magnetars or confirmed magnetars known so far. And as I said, only few of them are actually visible in the radio regime. And because there are so few, you can actually list them all on one page. So these are the 6 magnetars which are known to be emitting in the radio regime. The first one, called XTE J1810-197, which sort of describes where it is on the sky in right ascension and declination. This is the one I'm going to talk about. It was the first one that was detected in the radio regime. And then on the bottom of the list, I've noted one which already has been mentioned in the chat today. And I put 3 big exclamation marks behind it because there's something notable about this. And I briefly talk about that towards the end of the talk. How are magnetars formed? That's something that is still debated. The starting point is exactly the same as the same pulsar, not same as pulsar, should read same as pulsars. It's the contraction of the remaining matter after a supernova explosion. But what makes them different from pulsars? Why do they have such a high magnetic field? There are different theories. Probably the most supported theory is a magnetohydrodynamic process, kind of difficult to explain, but essentially it means that the rotational energy that this neutron star has is transformed into magnetic energy due to some circumstances in the very early phase of this formation of the neutron star. But there are also other theories, fusion of 2 neutron stars in an accretion model. So it's still open finally what the mechanism is. But we'll just take it as it is and see what can we tell about the magnetar that we have been observing. A little bit about the history of this magnetar. It was discovered in 2004 that a known magnetar, which was known from its gamma emission, that this magnetar also emits in the radio regime. There was the detection of a weak or moderate weak source at 1.4 gigahertz, 4.5 milliansky at the time. and it was located to be at the same position as this magnetar. That was in 2004, but was not detected at the time that that was actually a pulsing radio source. That was only detected a couple of years later when it was detected that there is a pulse radio emission from this magnetar, exactly with the same period as the X-ray and gamma ray emission. And that was the first time that a magnetar was identified to have similar properties to a radio pulsar. And of course, that attracted a lot of observation, and people started looking at that. The thing, however, was that while it was detected in 2006, it vanished in 2008. So sort of declined in intensity, and it disappeared. It was still visible in the higher frequency range or in the high energy electromagnetic spectrum. But as far as radio is concerned, this year is the decline. As you can see, the first detection in 2006 with about 10 millionsky, and then it rapidly declined and then sort of went up and down a bit, and then it disappeared. The crosses and dots and so on here, these are all attempted observations by various telescopes, and the level is showing what is the detection limit. So the Green Bank telescope had the highest sensitivity, and they did a couple of observations trying to find it, but it just was gone. Okay, so the skies were silent, and then at the end of 2018, there was a report from the people from the Jodrell Bank Observatory in the UK that they have observed an intense radio flare from this magnetar. So they saw the radio emission again, and they said it was intense. What I'm showing here is an astronomer's telegram that's sent out by observatories if there's something of interest where they would like other people to follow up and have a look. So some interesting sudden events. So we looked at that and said, okay, can we do something about it? Jodrell Bank in this report said, we see it with a signal to noise ratio of 400. And that's within 30 minutes of observation, for 30 minutes integration time. Jodrell Bank, that's a 76-meter telescope. They observed with close to 400 megahertz of bandwidth for 30 minutes. We didn't know the system temperature of that telescope at the time, but we made a back of the envelope calculation and said, okay, we have 25 meters diameter. We have 100 megahertz of bandwidth. If we observe for 60 minutes, we should get a signal to noise ratio of 31 if we have the same system temperature as Jodrell Bank, which we didn't know what exactly it was. We assumed we had a higher system temperature, which is certainly correct. At the time, we had 90 Kelvin system temperature. Just as a side note, today we have 35 because of some improvements that we have. Anyway, the back of the envelope calculation told us we should give it a try. So immediately when the source was up or above the horizon, we tried again. And that was then the next day after the astronomer's telegram. And sure enough, we immediately had this magnetar. We had a signal from the magnetar. Now this plot, some of you may be familiar with this type of plots. This the typical Presto type of plot, an evaluation of pulsars and of course repeating magnetars as well. So the left panel here shows the intensity over time, the increase of the signal to noise ratio with integration time. And you can see that all the time the magnetar was present. This is the accumulated profile shown twice. The panel here, that's the distribution of the intensity, again shown by a grayscale over the frequency. As you can see, this magnetar is a broadband emitter as expected. So That was clearly the Magnetar with the right period. And of course, we were happy to see that and say, okay, if that is something that's visible now, let's go and observe that more or less continuously. So we went on and just observed that. And this is an observation a couple of days later from the 16th of December, 2018. And you can see it's still there, about the same intensity. And when we further looked at the data, we found something interesting. We found that there was a single pulse, a strong single pulse, strong meaning it was strong enough that we could actually detect it as a single pulse in our data. The point, though, is you see a lot of single pulses in our data from radar, from RFI, from all sorts of things. So you need to verify that this pulse is actually coming from the Magnetar. And the way to show that it is coming from the Magnetar is showing that it has a dispersion, something that was talked about already in the previous talk. Now, this graph shows, first of all, the single pulse again. And then below that, there is a non-dispersed dynamic spectrum, as it's called. I'm not sure whether it's easy to be seen, but there is a line going, little curved line going across the spectrum. And this shows that the pulse from this Magnetar, in this case, the earlier arrival times are at higher frequencies, and at lower frequencies, the arrival time is later. So this is a typical behavior of a dispersed signal. And if you evaluate it, you'll find that that is exactly the expected dispersion from this pulsar. So this was the confirmation that this is actually a single pulse from the Magnetar. Okay, further observations. We continued the observations. And here are some examples shown from various times in the first quarter of 2019, or late 2018. And as you can see, it was always detected on these observations, but it got weaker. So the signal to noise ratio by the end of March is not as good as by the end of December. So there was a decline in intensity. Once we had seen this one single event pulse, of course, we looked for other single pulses. And indeed, on these days, on the end of December 29th, we actually had, in one observation, we had 2 of these single pulses. And on 1st of January and a few more, but not always. It's not the case that in each observation we had a strong single pulse, which we could detect as a single pulse. How did things go on with this? This is a calendar of the year 2019. And each day when we had an observation, we put a dot in here. If it's a green dot, it means okay, which means that the Magnetar was detected. If there's a red circle around the green dot, then we also had single pulses. You can see we had a few days when we had single pulses. You had already seen that the intensity did decline over time, and that continued into the year. So we had more and more days over time when we had non-detections. Sometimes it was weak. This is the light green color, but over time we had more and more non-detections. And sort of towards the last quarter of 2019, we didn't observe the pulsar, the Magnetar anymore. So we sort of stopped the observations then. Okay, said it looks like we're done with the Magnetar. It was an interesting exercise, but it's gone. Let's maybe have a look every now and then. But it's not interesting anymore. Story to be continued was, just as a side note, we had one observation in November where we saw the Magnetar again, The pulse was fairly broad at the time, but on the other days we didn't see much. Then there was another, after we sort of stopped the observations, there was another heads up that we got. In this case, it was from the Wollongong Observatory in Australia, when they said there's a resurgence in radio flux, so it's brighter again, and that was on the 30th of June in 2020. Unfortunately, at that time, we had some maintenance, so we couldn't start observations immediately. We had the receiver taken down, and we had to put things up again. So it was until July 23rd when we could start observations again, and we did that. And on the 23rd of June, we had an observation with not really a good result. It was something in of those cases where you say, maybe it's something, but probably not. But on the 2 days later, again, we had, on the average profile, there was not much to be seen, or it was questionable, but we had an interesting thing. We had a high number of strong single pulses with the right dispersion. Now, I have to explain that a bit, this graph. This is the observation which ran about for 3 to 4 hours. And this is the number of pulses, of single pulses detected, plotted over the dispersion measure. And you can see there's a clear maximum at about the right dispersion measure. And we had some fairly strong ones. Another thing that was striking for us, if you look at this plot, is that here you can see the single pulses, the sort of diameter of the circles denote the intensity, that we only saw them during the last part of the observation, which was a bit strange, but that was what we saw. So now we had a situation where we had a number of strong single pulses, but the average profile, so the average intensity, was actually not that great. Now, how did it continue? By the way, this is one of the single pulses. Again, the dispersion to be seen. A few days later, the intensity had increased. So we then saw the integrated profile again, and this was what it was looking like. So we had, again, our signal as we used to have it by the end of 2018 or early in 2019. So it had really re-brightened. And if you look at the single pulse activity from the same day, that is also very clear. I should mention that these pulses denoted here, this is RFI. But again, you see that at the beginning of the observation, there were not many single pulses or none, and then it increased, and it increased in intensity. And we were struggling with that. How come that the pulsar gets, sorry, I always say pulsar, I should say magnetar. The magnetar got stronger during the observation, always at about the same time. And because it was always at the same time of the day, it had to be an instrumental artifact. So we looked into that, and actually we found the reason. That was a mistake when we put the telescope back into operation. We have dual polarization. So we received in the two linear polarizations, and we made a mistake that we connected our back end only to one polarization, or actually twice to the same polarization. So we were looking only at one polarization, and what was happening, because it's a highly linear polarized source, it had to sort of turn into the right polarization angle during the day. So this is really the effect of the highly linear polarization that we see an increase of the observation. So that problem and that mystery was solved. But it sort of demonstrated, without that was done intentionally, it demonstrates that it is a highly polarized source. It continued. We talked about to other telescopes. We talked to the professional community, and they confirmed. John Beck was also observing, and they confirmed, yes, they see this extremely high activity of high single pulse activity. So we continued observation with a high cadence. And also we looked a bit at some older observations, and we found that sometimes we had overlooked a few things here and there, but we just went ahead and did very high cadence observations. Again, the calendar, when we resumed observation mid of 2020, and from then on, we had practically every day, we had a clear detection. We didn't observe on all days, but every time we looked at it, or most of the times when we looked at it, we had a clear detection of the magnetar and also a detection of single pulses. Now, talking about funny things, this are some highlights from the observations. So this is the integrated profile, and you can see that it changes on short time scales. So this is towards the end of August, where it's a single pulse. Then a second structure evolves within a few days and disappears within a few days. So this is just a matter of less than 2 weeks when this evolves and goes back. So there's a high variability in the profile. Then there was something which is still a mystery. These are 3 observations on 3 subsequent days, from the 10th of September, when we had a clearly high profile, high signal to noise profile, lots of single pulse activity. And then on 9/11, that's an infamous date, but it happened to be on that date, it was almost gone. We had a little bit of a profile here. No single pulses, these were just RFI events. And the next day it's up again. So the magnetar almost disappeared from one day to another and then came back on the next day. Of course, there was a high degree of suspicion that that was an instrumental artifact. But we have seen similar, I mean, we checked everything, looked into the log files and everything. And we couldn't find any instrumental artifact that could have created this. And we have seen similar events later on, even during an observation, that all of a sudden, within minutes, the magnetar turns on or can turn off. So these off and on events do happen. This is an example of a very bright single pulse. Again, the dispersion. This is a non-dispersed dynamic profile, can clearly be seen. Another interesting effect with this magnetar is that during a rotation, there may be multiple pulses within a short period of time. So these are 2 examples. There are 2 pulses within maybe 200 milliseconds. By the way, the rotation rate is 5.4 seconds. So that's a very narrow window in which these multiple pulses occur, or there's a triple pulse here. All these things happen, funny things. The further observations, we continued the observations, but there was a lot of data that we collected. We have, in the meantime, we have something like 18 terabyte of data, observation data from this magnetar. And fortunately, we have a student who did this, his master's thesis on the analysis of this data. Marlon Bowser is his name. His master thesis was studying the properties of the magnetar using Stocker telescope data. And the further graphs I'm showing, the further analysis have been done by Marlon as part of his master thesis. This is a plot of the evolution of the flux, described as signal to noise ratio from the 2 observation periods. The first one, when it declined, and the second observation period from mid of 2020 all the way into late 2021. And you can again see that the signal to noise ratio decreased and it went into almost non-detections. And then for the second observation, we had typically in the very beginning a very high signal to noise ratio, and that declined and sort of went up again and declined. The dots here, these are the observations that have been affected by this polarization issue when we observed only one polarization. So these, the data here should be taken with a bit of caution as far as the signal to noise ratio is concerned. But in what we basically can say, there was a very sharp increase in the intensity. So there's a strong evolution of the flux over time of this magnetar. What was the most interesting part were these single pulses that were strong enough that we can actually see them as single pulses. And because we have such longer observation times, we have collected something like 60,000 single pulses. And of course, these are very cumbersome to look at and see what are really magnetar pulses and which are artifacts like especially radar signals. And you can do that by hand or just look at each graph individually. So Marlon has used a program called Fetch, which is essentially a artificial intelligence, trained artificial intelligence program, which looks at the data, actually looks at a picture of the data. It looks at something which is called a bow tie diagram. This is the time of the pulse versus the dispersion measure. And of course, the magnetar has a specific dispersion measure, so it's then the timing is very narrow, and then it broadens as the dispersion measure is no longer correct. And this is called a bow tie diagram. And if there's a clear bow tie diagram, then it's a high probability that this is a dispersed signal. This is an example of a radar signal and the same bow tie diagram, and it looks different. And this program actually has a relatively high ability to detect these kinds of pulses. So it's very efficient. It's also used to detect fast radio bursts. And again, this is a artificial intelligence-based program. It's running on a GPU. And this has been used for analyzing our single pulse data. Just one example of a very bright one. This pulse has 640 Jansky. This is a dispersed dynamic spectrum. The little dots here in front, this is an instrumental artifact. Please forget about it. And this is the non-dispersed dynamic spectrum. In this case, the high frequency is up here, so it's the other way around as the previous one. And the red line is a comparison with theory. So this is a theoretical line. This is the way it is expected. And you can see it exactly matches the dispersion as can be expected. All right, looking a bit further at the single pulses and how frequently do they occur. I mentioned in the very early observations, we had only a very few. Every couple of days, we had a single pulse, which we could detect. Whereas in the phase 2, after the rebrightening, we had up to more than 300 pulses per hour. So that's a very high activity. It sort of follows the same graph as the overall intensity, but you see a strong variability there. So these are two very distinct phases of this magnetar. The average flux is about the same, but in one case there are only a few bright single pulses, and the other has lots of single pulses. So very different behavior of this magnetar. The occurrence of this multiple pulses, we found that over the full observation data set, about 18% of the rotations had multiple pulses, like this one. So the majority had just one pulse, but then there were some with 2 pulses, but some with 3, and even with 4. This is, by the way, a logarithmic scale. So in total, all multiple pulses are 18% of the pulse population. What we also observed is that over time, the width of the pulses changed. The different colors here are different parts of our observation time. So from 2020 September onwards, all the way into 2021. And in the beginning, the distribution of the pulse width is about the same, but in the later observations, there was the tendency that we had more narrow pulses. So there is also a change in the characteristic of these single pulses. Then also there was a change of the total energy of a single pulse. If you look at the energy that's in a single pulse, that was shifting towards lower total energies. So the graphs here, they are pretty much, oops, sorry, go back. This is about the same behavior once again. Whereas in the more recent observation, we have less energy in a pulse. I should mention that the vertical dotted lines, this is the completeness limits. So anything below that, there the intensity is too low that we can reliably detect that with our telescope. So you should ignore everything that's to the left of this so-called completeness limits. So this is where the really physics is, and this is more an instrumental effect. So this is really what you should be looking at, and the message is, over the period of time of observation, the pulses had less energy. So coming back to Jocelyn Bell, when she said magnetars do all sorts of funny things. Yes, they do. There's a strong variation of total intensity. There's a variation of the pulse profile. We have an occurrence of very strong single pulses, but how frequently they are, that is extremely variable. There are times in the lifetime of this magnetar where there are just a few. Every couple of days there's one. And then there are times like in mid of 2020 when there are a couple of hundred per hour. We have just seen that the single pulse change their characteristic over time. The energy changes. We see that multiple pulses can occur in one rotation phase. And the most striking thing is that this magnetar can disappear from one day to another, or almost disappear, and be back the next day. So as if somebody turns it on and turns it off. It is very funny that this magnetar does. Of course, the actual physics behind that, what's happening there, that's difficult to tell, and theoreticians will work on that and try to explain that and find out more about the characteristics. We are more on the observational side of things and see what can we detect and what can we experience over time. Now, why are magnetars so interesting? Well, they are interesting just because they're doing these funny things, but there's a little bit more behind it. The question is there any relationship between magnetars and fast radio burst? And there has always been the suspicion, yes, there might be a relationship. And this suspicion was very much fueled by the observation of one magnetar called SDR 1935 plus 2154, where in April of 2020, there was a detection of an extremely bright pulse from this magnetar. It's a confirmed magnetar, and it had not been observed in the radio before, but then there was an extremely bright pulse. Now, this was detected by several telescopes. This is the detection from the James telescope and another Canadian telescope. And there was a simultaneous detection of this event by the STARE-2 project. And from the observations from the James telescope and the STARE, the estimation is that these were in the megajansky range, so a megajansky bright pulse, extremely bright. And because it was so bright, that fueled the idea, yes, if a magnetar can be that bright, maybe FRBs are also magnetars. However, there are still orders of magnitudes in between in the brightness. So because magnetars are in our own galaxy, or this one which has been observed, it's in our galaxy, and the other FRBs are much further away, that's an indication but not a proof. So this is the open questions. Are fast radio bursts particularly an extremely strong pulses from the magnetar? I have put here side by side an observation from our magnetar and one of our observations from a fast radio burst. If you look at them, they look the same. This effect that we have, which I've shown before, multiple pulses with one rotation period, so a multiple structure, that's also something that we see in this fast radio burst. So this is another indication. However, on the other side, this magnetar is about 8,000 light years from us. So it's in our galaxy. And this fast radio burst that we have observed, almost with the same signal to noise ratio. It's also a very bright event that we are seeing. That's from a distance of 1.3 billion light years. So there is a huge difference in distance, and consequently, there are many, many, many orders of magnitude in the energy that's released. So that is still a discrepancy. I mean, this magnetar is not as strong as the SGR that I have just mentioned, but still there is a difference in the brightness in the orders of magnitude. So it remains an open question. Because it's an open question, that's a lot of motivation to look further into this magnetar, to look further into the fast radio burst, and that's something that keeps us busy for the time being. It's very interesting. And that concludes my talk. Thanks very much, and I'm happy to ask any answer any questions.
So one thing that is known about a lot of pulsars is that scintillation in the ISM can cause them to cause the apparent brightness to dim considerably over time scales of hours or days. Is some of this, with your magnetar observations, just scintillation in the ISM?
Well, we haven't seen any indication of scintillation in the magnetar. However, we do see that in the fast radio burst. And that's the reason why I just switched back to that. You can clearly see scintillation here. It's there's a structure in the frequency, and that changes. So if typically, well, this FRB had an active phase just recently for 2 months or so, right. And we saw about, in the most active phase, we saw about 1 event per day, and we always saw scintillation. We also had simultaneous observation with other observatories. When we compare notes, we have exactly the same scintillation pattern. We haven't seen any scintillation with a magnetar, but that doesn't really mean anything in the terms of, is it the same source or not, type of source or not.
Right.
Magnificent presentation. Thank you very much. On the left chart right here, I hope we could learn from what you've discovered. You say you have an artifact of the little dots vertically. Is that a mathematical thing, or is it electronic? Where in general does it come from?
It's a fault in the FPGA code of our spectrometer. There's a timing error in some of the spectral channels that displays the timing of some of the spectral channels. You see, they're equally spaced, and they're always the same amount prior. It's we have a FPGA-based spectrometer that provides the data, and there must be some error in the FPGA code.
All right, that's helpful. And so it's very local to your setup there.
Yeah, it's that specific instrument, and that's something that's not so easy to get rid of. By the way, you can also see the little bit of that here in this recording. That gave us some head scratching a couple of years ago when we had a precursor in giant pulses from the crab pulsar, and we were very excited about it until we found out it's an instrumental artifact.
That's helpful for us. Thank you.
So you and I should probably talk offline about FRB analysis chains, because we want to consider going to an AI-based chain as well, but we're not sure where to start. So,
yeah, sure, Marcus. Let's discuss that. That will be certainly a fun and interesting discussion. So I'm happy.
Sure. Okay.
I was going to ask you if the data sets are available for people to get if they wanted to take a look at like one observation day or something and do like an FRB chain or a Magnetar chain analysis themselves.
Yes, we can certainly provide some example data. The challenge with the exchange of data is the size of the files. We record 100 megahertz wide bandwidth with 218 microseconds time resolution. Typically, our raw data, even though we don't record IQ data, that would then be even more. It's typically 2 megabytes per second. What we can provide fairly easily is a short cut of a few seconds where the event is embedded. A longer, I'm happy to provide a longer time period as well, but then the challenge is how do you get the data across?
Yeah, you'd have to exchange hard drives or something like that.
Yeah, that's then
Okay.
you have to ship hard drives.
All right. Thank you.
Any further questions? Okay, David, I think it's time to give it back to you.